All right. Thank you, everybody who is joining us, and welcome to JMI TV. Another episode today. So today we're here to talk about Flexim. Most everybody knows about using ultrasonic Flexim clamp-on meters for liquid flow. By now, most people also know that you can take in a temperature input to do BTU metering and do some energy metering. But did you know you can use your Flexim ultrasonic for gas? Today, Steve Davis is here from Flexim with us to talk about gas flow, and is here to tell you what you can expect when you're looking to use ultrasonic to measure gas flow, limitations, strengths, and then afterwards we're going to unmute everybody, and we'd love to hear any specific questions that you guys have. So without further ado, Steve, I'm going to go ahead and transfer the control over to you, and feel free to take it away.
Good morning, everybody.
There you go. So,
we'll talk a little bit about Flexim today. If you're not familiar with Flexim, it's an ultrasonic flow meter company based in Berlin. Four shareholders own the company. Today we're going to talk specifically about gas measurement. And with gas measurement, it is the same theory of operation. It's transit time or time of flight. The main thing that's the difference here is the dampening material. And we'll talk about that a little bit. And the transducers, the type of wave that we use. So there are three principles we're going to talk about today to get a successful gas measurement. First of all, we have to have the right transducers. We have to do a proper installation. And when we look at our diagnostics, we want to get the best possible signal that we can get. So the right transducers really revolves around the Lamb wave type transducers that we use for gas. Lamb wave transducers are sized, the frequency is sized by the wall thickness of the pipe. So it's matched to the wall thickness of the pipe so that we can resonate our signal on the pipe wall of the transducer. This allows us to get some longer signals through the gas, which is not very dense. So with sound likes to travel through dense mediums like water and metal. It doesn't really like to travel through gases. So with gases, we have to do some things to ensure that we can get a signal through that light density medium. You can see here, these are the wall thicknesses that are for the different frequency of transducers over here. So this is basically the determining factor. OD is also outside diameter of the pipe is also a factor, but for the most part, we look at the wall thickness more than anything. This is Lamb wave, so this is what we're using to resonate this signal across. Oh, that didn't work too well. But we're resonating the signal across to give us a better chance of getting through this really light, dense medium here. Typically, we like to have about 80 psi of pressure in a metal pipe. Depending on the OD of the pipe, it has a lot to do with that as well. The farther the wave has to travel, the more density that we need in order to get a measurement or get a signal through the medium. Installation. So when we're talking about installation, we're talking about the dampening material. So because we're making a sound out of our transducers, that sound travels along the pipe wall and around the pipe wall here. These transducers are matched frequency transducers, so they're matched within, I believe, 0.01 hertz. So they're very tightly matched, which means that only our frequency from this transducer can really interfere with our signal and cause us a bad signal to noise ratio. What we use is dampening material. It's called Denzit. Denzit is used because it dampens this noise on the pipe so that the amount of signal is above the noise level. And that's simply because the pipe is way more dense than the gas. So the signal, the sound signal, likes to take the least path of resistance. So it likes to ride in this very dense metal. So if we only get, say, 10% of our signal across, and we have 40% of our signal as noise, we'll have a negative signal noise ratio. But we put this dampening on, and it decreases the noise on the pipe to be able to get us a positive signal noise ratio. The other thing I'll say about this is that you can see these flanges here. These are reflection points. So typically, we don't like to mount these transducers between 3 and 7 diameters of a flange. So either you're going to be farther than 7 or you're going to be less than 3. In a lot of situations, we don't have a choice. We have to go less than 3. But in some applications, especially distribution, we have long straight runs, and we can actually move these transducers out. So the challenges that we face with gas to measure standard volume flow is the compressibility and the low density of the gas. So compressibility has to do with standard volume flow. That's how much the gas will compress with pressure applied. So that is something that we kind of need to get an accurate standard volume flow measurement or normalized volume flow. And then low density gas, we talked about this already, but this has to do with the amount of signal that we can get through the pipe. So some challenges that we get a lot of calls for low pressure gas, a lot of boilers want to measure natural gas at the burner front. Typically, those lines are too low pressure for us to measure, except in a plastic or a non-metallic pipe, like polypropylene, PVC, things like that. We can measure gas pressure with gas pressures down to ambient or 0 psi. Some gases can be attenuating. CO2 is one of those gases. For us to measure CO2, it has to be a relatively high pressure, probably about 4 times the pressure of a normal gas. So in this case, we'd probably look at a line of CO2. We'd probably want somewhere around 300 psi to be able to measure CO2 or have a chance at measuring it. So the benefits of Flexim, it's basically the benefits of a clamp-on flow meter of liquid or gas. We're outside the pipe. So what that means is corrosive gases don't bother us because we're outside the pipe. Temperature or pressure. Obviously, the pressure can be as high as it wants to be, but we do have those minimums for the metal pipe. Temperature, typically in the past, we run up to about 130 degrees with the densite material. We also, Fahrenheit, by the way, and if we go higher than that, we actually have some dampening that we can paint on the pipe that's high temperature up to about 1200 degrees. And then we have transducers that'll go right up to around 320 degrees. And no downtime. That's the benefit of being outside the pipe as well. If you've ever had a demo or seen a demo done, you can do this without anybody even knowing that you're on the pipe because there's no process interruption. You don't have to do anything special to get a measurement. You just basically have to get on the pipe. And no downtime for installations. Basically the installed cost for a Flexim meter is, a tiny amount compared to an intrusive meter because we don't have to do really anything except run power and wiring to the meter. Straight runs. So we have a couple different things that we do for straight runs. This is a typical application that we see a lot of. Where the pipe comes out of the ground, runs a little bit through a valve possibly, and then it goes right back in the ground. So we don't get a lot of straight run in some gas applications, especially storage fields. And this is what we do. We do something called dual beam. So this is dual beam over here. You can see the 2 sets of transducers here. So what we're doing basically is taking a measurement and 60 to 90 degree opposing planes on the pipe, and we're averaging those to get an average flow through the pipe. This allows us to be able to be used in short straight runs and still be fairly accurate, 1 to 3% accuracy. This is dual quad beam. So this is something that we do quite a bit on the pipelines, on the bigger pipes. Basically, what that does is it does the same thing as a dual beam, but we're actually looking at 4 different planes now to get a better profile of the gas going down the pipe. With this type of measurement, we can actually get down to around a 0.5% accuracy or error. This is a mock-up here, so we do have some guys that actually put these on spool pieces and get them calibrated at CC or some other lab. And we generally get the highest accuracy from this quad beam, especially in bigger pipes. So when we look at the signal, the main diagnostic we look at for gas measurement is SCNR. So that is the amount of noise. It's the amount of signal that we're getting through the gas versus the amount of noise that we're putting on the pipe. So it's a correlated noise ratio, which means it's in the same frequency band, and it's actually noise that we're actually putting on the pipe. So for us, for a portal measurement or some sort of survey, to get 20 decibels, you're in good shape. You'll be able to get a decent reading. If you're getting good SCNR above 20, the SCNR doesn't really have anything to do with the accuracy, just is the amount of signal over noise that we're able to see. For permanent installations, we'd like to see the SCNRs, between 30 and 40 decibels. This allows for some leeway, such as some wet gas that comes by, a drop in pressure, things like that. You have some room that the meter has to drop signal and still maintain a measurement. Reflections, and we talked about that a little bit from flanges. 3 to 7 diameters is where you don't want to install from a flange. Obviously the pipe wall, so in order for us to get a good measurement, we have to have good contact with not only the transducer, but with the densite material that we're putting on the pipe. So flaky paint, pitting, things like that, we try to smooth out on the pipe. It can be painted, but it needs to be smooth. Okay, and insufficient dampening. So in some cases, the lower the pressure, the more dampening you have to put on the pipe, more densite you have to put on the pipe, because the amount of signal that we get through the medium at lower pressures is less than what it is at higher pressures. So sometimes we have to over dampen the pipe to be able to get to low pressures. So this is basically a picture of a window in a G721 meter, a permanent meter. And this is quality up here. This is SNR, which SNR is basically signal versus electronic noise. So that would be like bad grounding. Is typically one of the things that cause that, a low SNR. And then you have your amplitude of your signal here, which is the actual signal strength. And then you have the SCNR here, which is set, in this case, it's a bar graph. It says 78%. You can change these lines and see different things. You can actually see the SCNR. Sorry, I went the wrong way. You can actually see the SCNR number here in decibels by hitting a display button on the meter, and you can see the actual SCNR for both transducers. Next, here's the displayed measured values. So the other important diagnostic that we want to look for is sound speed. So the sound speed of natural gas, generally around 400 meters per second, depending on pressure and the makeup of the gas. But typically around 400 meters per second is what you would see for natural gas. So that's a good diagnostic. And what this diagnostic does is it tells you that you've installed the meter correctly. And that number can change if you put in the incorrect outside diameter, or if you put in the incorrect wall thickness, or if you mount the transducers and the spacing doesn't match what the meter asked for and you didn't tell it that you moved the transducers. So those three things are things that we can control to a point where we can make sure that our sound speed matches what it should. This is just one of the first meters that I did here at Flexim about 10 years ago. This is at a storage site, an underground gas storage site that Ameren has. Basically, we have a meter here that's measuring standard volume flow. We got a pressure and a temperature transmitter that go into the meter, and we're actually correcting for standard volume. With this meter, this is the older platform meter, the 704, not the 721, but essentially they do the same thing. And this is a common application. The transducers are actually down the pipe here a little bit, but this is a common application. In this case, we actually have another meter that's measuring this water leaving the separator. So they have to keep track of the amount of water they're putting back in the ground. So they monitor the gas with this meter after the separator, and they monitor the water coming out of the separator after it's been separated. So this is sorry, this picture is a little messed up. This shows the transducers mounted on a standpipe because it leaves the separator and the water goes through, I believe it's an inch diameter pipe. And we actually put a standpipe in here to keep this pipe full. And this is where we monitor the water leaving. And then this again is just a single channel standard volume flow. This is the transducer location right on the edge of the shanty. And this is pretty common. We do this for several companies. Sorry, the other thing I wanted to talk about was, I got time here. So this is typical application. The other common applications we have with gas would be odorizer pacing. So a lot of companies use us to pace their odorizers. And then the other part is distribution or compressor stations even, where they're monitoring gas coming into the station and gas leaving the station. And then on pipelines, we see a lot of check metering, where a customer is getting gas from another pipeline company. They have a custody transfer meter, the provider does, and then the consumer will use a Flexim meter as a check meter to make sure that they're not being overbilled. So this is just a quick session with Flexim. You guys have any questions?
All right. Thank you, Steve. I am going to take back control for just a second here. And everybody, feel free to put your questions in the chat. I'm going to unmute you guys right now so we can all talk. Also, if you'd like to go through the slides and review for yourself, if you had a question on a certain slide, you guys can do that freely now. So right at the top, where it says slide 20 out of 20, you can flip through them if you want to. Thanks again, Steve. Yeah, I'm going to grant mic access to everybody right now. So go ahead and unmute yourselves. And if anybody has a question, feel free to, we have our first question in the chat. Using PVC pipe, is it possible to measure lower pressures? Steve?
Yes, so PVC, polypropylene, plastic piping, anything that's not metallic, you can measure low pressures, all the way down to atmospheric, as a matter of fact. We use polypropylene for flare gas measurement off of tank flares. Yeah, non-metallic, PVC is basically a noise insulator, so it doesn't resonate that noise like a metal pipe would.
Okay, so PVC, you could go how low? Have you ever tried it?
Atmospheric pressure to 1 bar.
Okay, so all the way down. Cool.
Yep. We've occasionally measured some gases in vacuum, but not typically.
Okay. The next question is EtherCAT communication available? I think they mean Ethernet, but I could be wrong.
I think so too. So we have two protocols that we use. One is a building automation protocol called BACnet, and we have that both in RS-485 and Ethernet, or MSTP, and TCP/IP. And then we also use Modbus TCP/IP and Modbus RTU.
All right. So that would be a big yes, and I'm typing some of the answers in the chat as well, just in case anybody. Okay. Cool. Does anybody, just out of curiosity, are there any specific applications that someone would like to discuss or bring up? Maybe a challenging application. I have one in mind, but I was wondering if anybody had something that they wanted to talk about. Maybe they've tried Flexim or were considering it. Let's see here. Before I get to my story, Steve, I had a question for you, but there was another question that came in on the chat. You mentioned that water droplets would or could affect measurement. What diagnostics would help tell us if this was an issue or how much could be tolerated?
Well, with gas measurement, which is transit time, the same as liquid measurement, when we start seeing a second phase of medium, so if we start seeing liquid and gas, we have a couple of diagnostics that are indicators of a second phase called variable amplitude and variable time. Variable time can also be blow by, or if the velocity is being exceeded. But it's a really good indicator, along with signal noise ratio, SCNR. As you end up getting more gas, you're going to lose a little signal just because the refraction changes from a gas at 400 meters per second to a liquid at 1500 meters per second. So you start basically refracting off some of your signals, so you'll drop your signal noise ratio. It'll start dropping, and you'll start seeing this variable amplitude, variable time.
Okay. Good questions, you guys. Keep them coming. I had a question for you, Steve. So we all know that Flexim can do liquid measuring, and then we're here talking about gas measuring. And I have a customer that's sort of on the edge. They're not really sure at a certain part of the process if it's a liquid or a gas. I know that no flow meter, I think at least, no flow meter can do true two-phase flow. But what would be your recommendation if they weren't quite sure if it was a liquid or a gas, but they wanted to try and get a measurement?
So whichever phase is prevalent would be the way you'd want to measure. So if it's liquid with some aeration, or if it's gas with a little bit of liquid, you'd want to measure gas in that case. If it's liquid with a little bit of aeration, you want to measure liquid.
Mm-hmm.
Transit time can tolerate, depending on how much signal you have to work with. Transit time can tolerate about 10%, 5 to 10% aeration. So if you're talking about a gas or a liquid that's at its boiling point, or right at its boiling point, you want to be sure where you're mounting the transducers. You want to try to find a place that doesn't have pressure drops, or try to measure right behind a pressure drop, say a valve or something like that. Because if you drop pressure, most likely you're going to start gassing. If it's a liquid with some gases in it, there's no true way to do that. With liquids and gas, you can sometimes use something or Doppler mode. So if it's a liquid and it does have some aeration, and you can't seem to get a good measurement with transit time, you can put the meter in Doppler mode. And Doppler mode, you have to have bubbles, or you have to have particles or solids in the stream in order for Doppler to work. So that's an option. Not always does it work that well if you're starting to aerate too much, but it is an option.
Okay. Yeah, I know that in this case, the customer said, well, if you guys can't figure it out, we'll just put in a Coriolis meter. And I was like, well, and I appreciated the comment, but there are many diagnostics we have, and I don't think that would be the answer necessarily, would it?
Not generally. The only flow meter I've ever heard of that's a two-phase flow meter, which means it measures both the gas and the liquid as it goes by, is very expensive. It's an ultrasonic meter with several sensors. That's very costly. And for us, there's really no way to be able to quantify how much gas is going by, or how much, basically if it's set up to measure liquid, we're really only going to see the liquid that's going by. Or if we're set up for gas, we do have something called a wet gas compensation, where if you know what the percentage of, the LVF of the gas, then you can actually program that into the meter, and it will actually subtract that gas or the liquid from the gas measurement. So you'll get a true volume flow of gas minus the liquid.
Okay. Well, thank you everybody for joining us. That has been about a half an hour, and we really appreciate your time. Enjoy your lunch. Feel free to join us next week when we talk about pressure transmitter installation, the right way to do it and the wrong way to do it. So thanks again, Steve, for joining us. Thanks everybody else, and we'll see you next week.
Thanks for having me.
Yep. Bye-bye.